Okay, so welcome. Today we're going to be talking about thermodynamics, and to start off with, we're going to just discuss a little graph. So if we plot the number of molecules versus the average kinetic energy, so we're putting k bar on this axis and then the number of molecules on this axis. For particles that are moving at a greater average velocity, they're going to have a greater average kinetic energy, but that also means that there is a greater greater number of energies that those particles can be moving at. So what we end up seeing as we plot this distribution, the histogram for this would look something like so. So if there is a greater peak, that means there is a greater, so let's say K1 bar, there's a greater peak, but also there's a wider variety of velocities that these particles could be moving at, so there's a greater number of kinetic energies these particles can possess. Whereas if a sample is at a lower temperature, it is going to have a greater peak, but the value for that average kinetic energy, so let's say k bar 2, is going to be much smaller. So whatever this number is on the 2 side is going to be less than the value on the 1 side. So all we see is that the sharper the peak, that the lower the kinetic energy, meaning that this is going to be a cold substance and this is going to be a hot substance. Okay, and while we're speaking of hot and cold, if we put a hot object next to a cold object, what we know is that by conduction, they are going to transfer energies. And so basically what you have, you can envision one particle that is going faster on average colliding with another particle that's going slower. It's going to transfer some energy and momentum to that. And the reverse process could occur, that one of these cold objects can be moving faster on average than one of these hot objects, but just the latter case is going to happen far fewer times. So there's going to be smaller amount of the cold transferring to hot. So what we see is that there is a net flow of energy, which we call heat, that is going from the hot to cold. So in general, what we say is that the temperature, the average kinetic energy, that flows from the hot object to the cold object. Now we're also going to be talking about internal energy. And internal energy can be calculated by 3/2 nRT, which also can be calculated by 3/2 big N times KBT. And more importantly, we are typically talking about a change in internal energy. So this could be a change in temperature, as so. And like I said, we're talking about conduction, so that is the mode of heat transfer when the objects are actually physically making contact. And there's an equation in your reference tables that delta Q over T, the rate of heat flow, is equal to K times A times delta T divided by L, where K is a constant of that property. We call it a conductivity constant. A is the surface area that's making contact. The temperature difference is self-explanatory. And then L is the length of material that's between the two. So the thickness of the material. So the thicker the material, the slower the heat transfer. The greater the conductivity constant, the greater the area, the greater the temperature difference, the faster the rate of heat transfer. And this makes sense that if you have something like aluminum, well, aluminum has a very high K value, so it transfers heat very quickly, which is why when you touch a piece of aluminum, it might feel cooler than something like plastic, but even if they've both been sitting in a room for a long period of time, so they are at the same temperature, that's because it will transfer the heat out of your hand at a much faster rate, making your hand feel cooler. So another thing that we can talk about is the RMS speed. So as I just mentioned that there's an equation for internal energy. Well, if we're just talking about the kinetic energy of the particle, we have the K value, the average kinetic energy, E being equal to 3/2 KBT. So this is for one individual particle. Okay, so notice that the N factor was dropped from this. And What we could also look at is that we know the kinetic energy of a particle is also 1/2 mv squared, so the average kinetic energy would be calculated 1/2 mv bar squared. So if I set these two equal to each other, and cancel out the 2's there, and solve for v bar, what I end up seeing is 3 kBt divided by m, and the square root of that is equal to the square root of v bar squared. So this is the square root mean squared. So we call that is the RMS value for the velocity. So if you want to figure out the root mean squared velocity of some material, and it's at some temperature, and you know the mass of that material, you can figure out the root mean squared from that. Now, when we're talking about an ideal gas, we know the ideal gas law, which is PV equals nRT, which is a very useful equation. And you will also notice that your reference tables has it equal to NKB times T. So if you are given the number of moles, use the one on the left-hand side. If you're given the number of molecules, the number of molecules, use the side on the right-hand side of that equation. And so this actually has some interesting consequences, and you remember from your chemistry days that you had a P1 V1 over T1 equals P2 V2 over T2. And the way that this was derived was that if you rearrange it, PV over T is equal to NR. And as long as your gas sample stays the same, the N value, the number of moles, will be the same, and R is always a constant. So basically, if you take the pressure, multiply it by volume, and divide it by temperature, it remains the same. So that's where this equation on the left-hand side came from, or where this came from. The first law of thermodynamics is that the change in internal energy is equal to Q plus W. And this makes a lot of sense, that the way that you change the internal energy of a substance is you either heat it or you do work on it. And what's interesting is that this often relates to PV diagrams, because the PV diagram, the area underneath, so if I consider 3 points, the area underneath this line is equal to the work, and actually more explicitly it's equal to the minus of the work. So there's 3 points A, B, C, and let's say the process looks something like so. A goes to B and then B goes to C. Well, the work done is equal to minus, on the gas, is equal to minus P times delta V. And when you look at the delta V from A to B, since the V is not changing, the work done on the gas is 0. So if I'm looking at this equation, the first law, if the work done on the gas is 0, then the change in internal energy must be equal to the heat transfer. And if I know the values of the P and V, let's say this goes from 1 to 3, and this is 1 cubic meter, and this is, let's say, 4 cubic meters. And so I could say that when it goes from A to B, it triples the pressure and keeps the volume the same. So looking at the equation at the top here, if we triple the pressure and keep a constant volume, and N and R are the same, then it's going to have 3 times the temperature. So if I know that this is at 100 K, then that's going to go up to 300 K, 3 times the original temperature. And so I can calculate that delta U by that delta U equaling 3 halves N R delta T. And if I know the change in temperature, then I could figure out the change in internal energy, which then I can in return figure out how much heat must have been transferred in order for that process to happen. And you can see here that the delta T is positive going from A to B. It got warmer, so delta U is positive, so that's a positive number, and then that means that Q must be positive. And so here's my biggest suggestion when you're looking at PV diagrams, and we'll talk about some specific processes in a second, is that you're going to benefit significantly by talking about the processes that are happening. So A to B, then B to C, and let's say C went back to A and made some sort of cycle. So that's the process. If you talk about the change in temperature with the change in internal energy, the heat flow, and then the work done on the gas. And the work done on the gas is calculated by minus P delta V. The change in internal energy is 3 halves N R delta T. And the heat flow is the change in internal energy minus the work done. Okay, so, and then the delta T is just a straight subtraction. So organize your ideas, because on each line you can apply the first law of thermodynamics. Okay, and then better yet, the total. You could talk about the whole process, so the whole cycle. Okay, so you can apply the delta U equals Q plus W to any particular part. So if you're given the heat flow, so let's say you're told that this is plus 100 and A to B, let's say, is an isothermic process. So let's say you have A and then we have B right here, and that's an isotherm, meaning that they're at the same temperature, meaning that the change in internal energy is 0 and it's flowing in that direction. Well, notice that if there's positive heat added to the system, well, and so this is 0 and this is positive, then I know that that must be negative in the same amount. Then I can know that this must be minus 100 joules. And what you will also notice is that when delta V is positive, the work done on the gas is negative. So if this is positive, you have a positive times a negative, so that makes this negative. So more times than not, it's just a matter of knowing the sign convention that will help you answer a particular question. And so just lastly, just some definitions about some different processes. So if we have a process, let's say A to B, that is keeping a constant pressure, we call that an isobaric process. If it goes from B to C, it's keeping a constant volume, we call that an isochroic or isovolumetric process. And then if it's going from A to C and it's going along an inverse line, we call that an isotherm or isothermal process. The other ones that we might see is an adiabatic process, which an adiabatic process may look like, actually I'll put it on the same diagram here. It may look something like that. So we have some sort of curve, and let's say it's going in that direction, but it's not an inverse curve. And so remember that you can tell an inverse by looking at these values. If it goes from 2 to 1, and then it goes from 1 to 2. So it's cutting, so in this case, the volume is being cut in half, but the pressure is being doubled. So one goes down by a factor of 2, one goes up by a factor of 2, isothermal. An adiabatic, some key words that you might be looking for an adiabatic process is that there is, it's done very quickly, or it's in a well-insulated container, because what that means is that the heat flow into the material is 0. Okay, so you would end up seeing that there is 0 Q. So that means for an adiabatic process, the change in internal energy is equal to the work done on the gas. Okay, so that's all for today. Thanks for listening. I hope you've enjoyed and learned something. Have a good night. Bye-bye.